Hello students, in today's session we will be talking about equilibrium conditions for rigid bodies. Lecture is designed like this. We will first talk about what is equilibrium, we will talk about rigid bodies, and subsequently we will talk about condition for equilibrium. We will also define what is a reaction force, how to define it and so on. We will draw free body diagrams and we will end the session by giving tips for solving problems. This presentation comprises of certain video and video files embedded in a PPT. So you will find it interesting. You will be moving out of the presentation and coming back into the presentation quite often. To start our presentation, let us define what is meant by equilibrium. A body is in equilibrium if both the linear and angular acceleration are 0 with reference to any inertial frame. That is, the object is at rest or it could be moving. If it moves with a constant velocity. In case of static equilibrium, the body is at rest with the selected frame of reference. A good example for static equilibrium is the tug of war. In case of tug of war, which you would have played in your school days or in your college, wherever it is, you will see that the force is applied by two teams, both are pulling in the opposite direction. If the net force is 0, then participants don't move, the cable or the rope tends to be at the same point. This is a good example for an equilibrium condition wherein the forces are collinear and concurrent. So you will also have an understanding on what is meant by collinear and concurrent. Forces acting along a straight line is collinear and concurrent is passing through a particular point. Here it is straight line and it is passing through the same point. While what is going to happen is not all systems are collinear and concurrent. There could be non-collinear and non-concurrent systems, like I have shown in the other example, wherein a rod of a given length is subjected to numerous forces acting at different points. The forces could be, they are not acting at the same point, so it is non-concurrent, and they are also not linear, and they can also be non-coplanar. If the net, here in this case, the net force and the net moment is equated to determine the equilibrium condition. So these are a few examples to tell you what is meant by equilibrium. We will proceed. We will talk about what is a rigid body. Solid body which does not deform or undergoes zero deformation is called as rigid body. And to identify a body is rigid, the distance between two given points remains always constant irrespective of the forces acting on them. There is a small video which tells you what is a rigid body is.
So far in the course we've been studying the motion of collections of particles. We would now like to consider rigid bodies. Now, rigid bodies can be translated in space as I move it like this, or we can rotate this rigid body about some point. I can rotate it about the end point. I can rotate it about a point which we call the center of mass. So I can rotate it about the center of mass. I can take the rigid body and I can rotate it about the center of mass and also translate it in space. So there's many types of motions that we can do with rigid bodies. Sometimes the motions are quite complicated. If I spin it like that, it is a very more complicated motion. You can see that it's rotating about this axis. So what we'd like to do now is analyze how to think about the motion of rigid bodies. And what we'd like to do is idealize our rigid body. So let's just draw, even though we looked at a rod here, let's just draw some extended idealized rigid body. And let's identify 2 points in that rigid body, the jth point and the kth point. And we'll think of our rigid body as a bunch of point-like particles, mj and mk. And the important thing that defines a rigid body is the condition that the distance, and we'll draw this a vector from the kth particle to the jth particle, so we'll draw that as r, j, k. And actually I would like to write it from the kth particle to the jth particle, r, k, j. And our condition is that the magnitude of this vector, which I'll denote as rkj, is constant for all points j and k. Now, what does that mean? That means the distance between any 2 points in the rigid body stays fixed, no matter how the rigid body is moving, and no matter what 2 points I choose, the distance between any 2 points is fixed. So we'll rewrite this as the distance between any 2 points is fixed. So that doesn't change. And that's what we call the rigid body condition.
Condition for equilibrium of rigid bodies. So for a rigid body to be in equilibrium, the sum of forces acting on it should be 0.
And that includes the x direction,
You can watch
the
this
y
video.
direction, and even though we don't talk about it too often, the z direction. Right and left, y is up and down, and z is kind of like the back and the forth towards you or away from you. Also, for rigid objects, all torques have to be balanced at all pivot points. When we start solving problems, you'll see how this can be very helpful. But in terms of an equation, it's the sum of the torques has to be equal to 0. Now, in terms of a general strategy, the first thing you have to do when you approach a static equilibrium problem is to identify all forces with their locations. If you accidentally leave some forces out, you could end up getting the wrong answer. And this is the same as when we had force diagrams back in motion in 2 dimensions. Don't forget your pivot point forces. Sometimes there are forces holding a particular pivot point as a fixed point, and there's got to be forces to do that, even though we may not think of them as being applied forces at that point. After you know all your forces, then we can construct our force equations. Then we construct our torque equation. You have to do some algebra, plug in your numbers to do the math, and as always, check your answer.
And then perform the algebraic operations to get your answer. So that is what is mentioned in this. Sum of all the forces acting on the rigid body should be 0. This concept is applicable for a system which has collinear and concurrent forces, while sum of forces and the moment should be 0 if the system is subjected to non-current forces. We will move on to the next slide, wherein we will talk about what is meant by action-reaction pairs. According to Newton's third law, which says every action has an equal and opposite reaction. So what is a reaction, how is it, and what is its value, and these are the things we will be seeing this in this slide. We have a small video which I will play to have an understanding on what is the normal force means.
Now we can consider the normal force. So our first question is, what do we mean by normal force? Let's start with one word at a time. Force, we've already talked about, is a push or pull on an object. So then we get to normal. Now what we don't mean by this is it's not an ordinary force. While they happen all the time, that's not the usage of the word normal we mean. Instead, we're talking about a mathematical definition of normal that refers to the perpendicular. So for example, if I have a surface, my normal force is always going to be at a 90-degree angle perpendicular straight out from that surface. And I use the F with a sub n as my symbol for it, both capital F and capital N. So here's some examples. Again, if I have a horizontal surface, my normal force might be straight up from that surface. If I have a vertical surface, my perpendicular is going to be, say, out to the left. And if I have a sloped surface, my normal force is still going to be perpendicular, but that means it's going to be off at an angle. Now, when do you have the normal force? Anytime you have solid surfaces in contact with each other. The normal force is the force that prevents those solid objects from going through each other. Now, from Newton's third law, we know that forces come in pairs. So let's understand that in terms of a normal force. The ground pushes up on the block with a normal force, but the block also pushes down on the ground. If I push on the wall to the right, the wall pushes back on me to the left. These are force pairs. I push on it, it pushes back on me. In both cases, I can't push through the wall and the wall doesn't push through me. Now, if I've got multiple surfaces, like I have in this example, I have to consider a normal force for each one of the points of contact. So for example, up here at my hands, I have a normal force where I'm pushing on the wall and the wall is pushing back on my hands. In this case, my front foot is going to have a second normal force where my foot pushes down on the floor and the floor pushes up on that front foot. And in the back foot, we have a third normal force. And again, it's a force pair where my foot pushes down on the floor and the floor pushes back up on my foot. If I have multiple objects, I need to consider the surfaces for each one of those objects. So here I've got two boxes sitting on top of each other, sitting on the floor. Well, there's a surface between the two boxes, and so the green box pushes up on the blue box, but the blue box is also pushing down on the green box. And there's a surface contact between the green box and the floor, so that the floor pushes up on the green box and the green box pushes down on the floor. When I go to do force diagrams, remember that I want to treat each object separately. So my blue box has a normal force upwards due to the green box, and my green box has two normal forces, one due to the floor and one due to the box sitting on top of it. Now don't forget, both of those boxes also have a force of gravity, assuming they're sitting here on Earth and not out in space. And so your full force diagram would have to take into account not just the normal forces, but any other forces that are on there as well. So that's your introduction to the normal force.
I hope this introductory video on normal force should have given you a good understanding on what is meant by normal force. Normal forces are always normal to the surface. It is an action-reaction pair, and it is equal to the force with which the body presses the surface and the surface gives the normal force. The normal force plays an important role in determining the equilibrium of conditions. We'll see how to construct a free body diagram, taking all these normal forces, the forces acting in the system, on the system, and subsequently solve problems. So the next video, the next slide, will be talking about free body diagram, and you will also have a small video that tells you how to construct a free body diagram.
Now we will see free body diagram. This free body diagram is an important concept in the engineering mechanics. What is that importance is to find the different forces that are acting on your body, to evaluate the forces acting on your body whenever it is in stationary motion, in a stationary state or in a motion state. We have to draw the free body diagram. And most of the bodies, or all of the bodies, are rigid bodies in engineering mechanics. We treat them like that. So to evaluate the forces and to find the resultant of the forces, we have to draw the free body diagram. This free body diagram is representing the body which is free from the support reactions or wall reactions like that. Suppose, see this is a simply supported beam, and this simply supported beam is carrying certain loads like this. To evaluate the resultant of these two forces, or how the beam is stationary, to find that we have to remove these supports, and these supports are replaced by their reactions. So the free body diagram of this beam, it is like this. So these are the two support reactions. Say if these ends are A and B, then this is a reaction at A and this is a reaction at B, and say these are the two loads acting on it.
So in a free body diagram, you draw the object under consideration. That is, draw the body under consideration, separated from the system, include all the forces that acts on the body. The forces could be normal force, the friction, tension and the spring forces along with the weights which apply to the system, apply to that particular body for which you are drawing the free body diagram. Do not include, there's no, you need not have to include the net force, because having shown all the forces, it is not necessary to calculate the effect of the net forces. And what you can do is subsequently resolve each of the forces into the x and y component if it is a planar system, or x, y and z component if it is on a three-dimensional body subjected to a three-dimensional force, 3 dimensions, and subsequently do this iterative process for the other objects within the system and try to draw the arrive at the equation of the system. We will continue with the video.
So these supports are replaced by their reactions. Likewise, suppose if a sphere, it is hanging from a wall with the help of a wire which is connected to its center, then its free body diagram is like this. Say this is the weight of the object and this is the force. We treat it as a tension. That force or tension in the string, and this is the reaction of the wall. Here the sphere is pushing the wall and hence the wall applies a force on the object or on the sphere. So these are the different kinds of forces that are acting on the object. So these are called as free body diagrams. Whenever we have drawn the free body diagrams, then only we are able to find or evaluate the forces. Here, suppose we want to find the tension in this spring or tension in this steel string. To evaluate the tension, we have to find the different forces that are acting on the object. Here, this is the diagram given. From this diagram, we cannot find what are the causes or what are the forces that are acting on this object to be stationary. So by drawing this free body diagram only, we can find the different kinds of forces, that is the tension in the spring. So here the tension in the string, it is like this. Then by using the equations of equilibrium,
to construct a free body diagram. Having constructed the free body diagram, now write down the equations of the system and solve it for the solution.
Directions. But if I put another mass on to do the math, and as always, check your answer when you're done.